Data unfolding, the process of removing noise or artifacts from experimental measurements, lies at the heart of scientific discovery across physics, astronomy, and beyond. In particle physics, especially at the Large Hadron Collider, unfolding is essential for measuring differential cross-sections, precise predictions that link raw detector data to the underlying laws of quantum field theory. Traditionally, this task has been approached using the Richardson-Lucy deconvolution method, which minimizes the callback, labeler divergence between the observed data and the forward-modeled noisy output. But this approach relies on a subtle and often violated assumption that the measured data and the model output must have overlapping support. To enforce this, practitioners resort to binning, discretizing both the data and the noise model on a grid. While practical, this introduces numerical artifacts, biases in derived quantities like moments, and suffers from the curse of dimensionality. In this work, we propose a radical alternative, replacing the callback, labeler divergence with a Wasserstein loss, a geometrically motivated distance rooted in optimal transport theory. This shift unlocks a new paradigm in unfolding, one that does not require absolute continuity between the measured data and the model, respects the intrinsic geometry of the data space, and avoids the pitfalls of binning. Let's define the unfolding problem formally. We are given a measurable space x dollar, representing the true signal, and y equals \math bar d dollar, the space of observed measurements. A noise model is represented by a Markov kernel \rho, x to \mathcal p, y dollar, so that for any x in x dollar, the measurement at x dollar is distributed as \rho x dollar. The forward model maps a true signal sigma in \mathcal p, x dollar to a noisy measurement \nu sigma dollar, defined by int yf, y d nu sigma, y equals intex left int yf, y d rho x, y right d sigma x. Our goal is to find the true signal sigma dollar that best explains the observed data nu in \mathcal p, y dollar solving. Sigma in arg min sigma in \mathcal p, x, wpp, nu sigma nu. Where wp dollar is the p dollar Wasserstein distance, quantifying how much work is needed to transport mass from nu sigma dollar to nu dollar. This formulation removes the need for absolute continuity. Even if nu dollar and nu sigma dollar have disjoint supports, a common scenario when detectors have limited resolution or when signals are sparse, the Wasserstein distance still provides a meaningful, geometrically intuitive measure of discrepancy. But beyond intuition, we establish sharp theoretical guarantees for existence and uniqueness of solutions. We introduce two key conditions on the noise model \rho dollar. CTY, x \mapsto rho x dollar is continuous in the narrow topology. CRC, the map x \mapsto MP, rho x dollar, the p dollar th moment of rho x dollar has totally bounded sublevel sets. Under these assumptions, we prove that a minimizer always exists, even in infinite-dimensional spaces. Furthermore, for p1 dollar, and when the measured data nu dollar is absolutely continuous with respect to Lebesgue measure, we show that the minimizer is unique if, and only if the mapping sigma mapsto nu sigma dollar is injective on the set of minimizers. These conditions are not just sufficient, they are sharp. We construct counterexamples showing that removing any one of them can lead to non-existence or non-uniqueness. This resolves an open question posed by Lee et al. Regarding transport map noise models, where nu sigma equals phi sigma dollar for a measurable phi, x to y, and provides a complete characterization of when such problems are well posed. To compute these minimizers, we develop a provably convergent generalized Sinkhorn algorithm. Unlike classical methods, this scheme operates directly on empirical observations of the noise model and measured data. It avoids parametric assumptions on the measures or the Kantorovich potentials, relying instead on Bregman projections in the space of probability measures. The algorithm works by solving an entropically regularized version of the Wasserstein minimization. Sigma \virpsilon in arg min sigma wpp nu sigma nu plus \virpsilon text kl nu sigma hat m plus \virpsilon text kl sigma hat sigma, where hat m hat sigma dollar are reference measures. Crucially, this leads to a finite-dimensional convex optimization problem when the measures are finitely supported, a natural setting in particle physics applications. We then reformulate the problem as a dual optimization over scaling variables, enabling a Sinkhorn-type iteration that scales only with the number of data points, not the ambient dimension. This makes it highly efficient for high-dimensional problems like jet mass unfolding. In our numerical experiments, we compare this optimal transport unfolding method with classical Richardson-Lucy deconvolution. We test both one-dimensional and two-dimensional problems inspired by real-world collider physics. In the one-dimensional case, we simulate a Gaussian mixture signal corrupted by a transport map with additive Gaussian noise. We vary the number of samples per point m dollar and the number of bins n\text bin dollar used in the RL method. What we find is striking. OT unfolding achieves higher accuracy across all configurations, especially when the noise model is coarse. That is, when $m is small. In these cases, the overlap between \new dollar and \new sigma dollar is minimal, violating the KL divergence's assumptions. RL struggles, showing non-monotonic convergence and strong sensitivity to binning. OT, by contrast, remains stable and robust. Even more telling is the performance on physical observables: mean, variance, and the ratio \Langle x1/x2 \Rangle dollar, which is sensitive to hadronization effects. While RL results depend heavily on the choice of binning, OT delivers consistent, accurate estimates, independent of grid choices. In the two-dimensional jet mass unfolding problem, generated via Pythia and Delft simulations, we see the same trend. OT consistently outperforms RL, particularly when the noise model is poorly resolved. The benefit diminishes as $m increases, not because OT loses power, but because the binning artifacts that plague RL become less severe. This suggests a fundamental advantage. OT unfolding is not just more accurate, it's more principled. It doesn't depend on artificial discretizations. It respects the geometry of the data space. It avoids the need for absolute continuity. And it naturally handles sparse, high-dimensional, or discontinuous distributions. Moreover, our algorithm converges at a known rate, thanks to recent results in Bregman projection theory, and can be implemented efficiently using logarithmic coordinates to avoid numerical overflow. So where does this leave us? The Kullback-Leibler divergence has long dominated unfolding because of its connection to maximum likelihood and the M algorithm. But it comes with hidden assumptions and fragility. The Wasserstein loss, by contrast, offers a more robust foundation, one grounded in geometry, stability, and theoretical soundness. We conclude that optimal transport provides a superior framework for data unfolding, particularly in modern, high-dimensional, and unbinned analyses. It answers long-standing open questions about existence and uniqueness. It enables scalable, provably convergent algorithms. And it delivers higher accuracy, especially in regimes where traditional methods fail. Future work will explore stability under perturbations, convergence of discrete solutions to the continuum limit, and application to real-world, unbinned measurements in high-energy physics. But for now, the message is clear. When the data is messy, the noise is complex, and the grid is too coarse, turn to optimal transport. Because in the end, the goal isn't just to fit a model. It's to recover the truth, not through binning but through geometry. Not through assumptions but through mathematics. And that, perhaps, is the real power of unfolding.